Brandon Rhodes.
Well, everybody, welcome to PyOhio 2013. I hope you enjoy the 2 days that we'll spend together here on the campus. I want to talk about a number of topics in Python, from simple to fairly complex, that all revolve around why can I get things done in this language? Why can I, or why at least do I perceive myself, to make fairly good progress and accomplish things when I'm using this particular language? And I'm going. The examples are going to be a mix of very simple and very advanced things, because I've noticed in the past that PyOhio is, in terms of the ability of the people who show up, perhaps the most diverse conference that I attend during the year. The only conference I attend that's on a university campus, and that is free. It's amazing the difference between a conference that is even $5 and a conference that is free for students. Who here knows what I mean? And so people show up here who might not even be programmers, who might be new to Python in particular. And by hitting, hopefully, a range of complex and simple topics, I hope that there's something that each of you get out of this keynote as I talk about why Python keeps me productive. I called it sine qua nons. A sine qua non is something without which you can't just do work. It means without which, nothing. It's the sort of thing you need that's your baseline requirement in order to get moving. And so we're going to survey a number of the things without which I would more frequently hit roadblocks and would not be productive in my programming career. To get us all on the same page, there's certain tooling that I recommend anyone working in Python learn to set up. Whatever your editor of choice is, there should be a way to hook in Jedi, which is a great completion and documentation engine, so that you type the name of a built-in method and the docs just come up to remind you what to type next, instead of your having to constantly flip over to documentation in your browser. I always hook up PyFlakes to my editor of choice because it will tell me when I hit save, before I even go run the code, if I've misspelled a name and I'm about to get a name error or an attribute error when I run my code. That saves at least hours a year. I won't exaggerate and say weeks and weeks of my year, but at least hours a year are saved by really stupid mistakes I make being immediately flagged. And I always recommend that people learn virtualenv, which is a little container technology that under any given project you're working on lets you create a bin, an include, and a lib directory with its own little Python and its own set of dependency packages that you install. This is a lifesaver if you happen to, on your hard drive, have, let's say, a Django 1.5 web app that you're writing fresh for a customer, but then another customer calls up, or you want to pull up an old project you've used that used Django 1.4. Obviously, both of those are not likely to install system-wide. One or the other would have to be installed if you became the administrator and ran an install command. But thanks to having a virtualenv per project, each project can have its own dependencies at exactly the versions it needs. When you're done with the project, commit it to version control and remove the directory. All those things are gone from your hard disk. So that's a tool every Python programmer should experiment with. In conjunction with that, if you keep a little requirements.txt file in each project where you record the different dependencies that your project needs, then a single command, pip install -r for requirements, requirements.txt, will get a project that you've checked out of version control back up and running with the tools it needs. So that is the very first sine qua non that I find I can't do without. Project sandboxes, so that instead of a big bloated system directory with dozens of out-of-date modules that I installed that one time to experiment with that are now years old. I instead have small agile project sandboxes set up, each of them with the exact requirements of a particular project. So, moving on from the tooling, the environment, the sandbox, what features does a language itself need in order to keep me productive? A lot of this material just comes from having watched myself code, metaphorically I mean, over the last few weeks. I didn't set up a mirror or anything like that. But I tried to think about what I was doing each day to notice what features of Python kept me the most productive. At a very basic level, I'd like to talk first about container types. The fact that Python comes built in with simple, supported in the built-in syntax containers that can either keep up with a sequence of items, we use a list, or that can let me index one kind of data using as an index another. And in Python, that is called a dict. Other languages call it a hash. Under the covers, it's implemented the same way, no matter what your language happens to name it. There is a whole other talk that could be launched into right here on the things you can get done quickly with the fact that iterables and iteration in Python is composable. Every kind of container, everything that does an implicit loop over a series of items is built to exactly the same specification. So like Lego bricks, you can pile them up and fit them together without a second thought. Here is a simple example of whether a generator that is looping over all students and only selecting the ones that haven't graduated pulls out the surname of each student so that I can then send that stream of surnames into the set built-in type, which eliminates duplicates and will tell you that it saw Smith only once, no matter how many times that was submitted in the incoming stream. And then a set can be iterated over. In this case, I pass it to the sorted built-in, which gets whatever it's told to iterate over and sorts it into a list. And so, with just a line or two of code, I get a sorted, deduplicated list of surnames for not graduated students, a process that can take several loops and have a lot of roadblocks and mistakes you can make in other languages, especially lower level languages from which a lot of Python programmers come as the first language that they learn. But I'm not going to go into this in any further detail because it's an entire keynote of its own. In particular, it's the keynote that core Python developer Raymond Hettinger just delivered 3 months ago at PyCon out in Santa Clara. So if you want an excellent survey of the way that iteration and all of these pieces built into Python work together, just go online and look up Raymond Hettinger's keynote, and you'll get lots more information than even I could cover here today. So that kind of had more to do with lists and sequences. How is a dictionary, especially for those of you who are really new, how is a dictionary really used in practice? What advantage is it to have this idea of a mapping or a hash table that lets you jump from one kind of data, like a string that's a key, to some other kind of data? And I want to actually unpack for you and show on the screen the most fundamental, larger scale maneuver that you can perform with a dictionary, which is a data operation called a join. How many of you have ever heard that term before? Good. Several of you have your hands down and will not be bored. Let us imagine that I have 2 text files full of data. On the right, students.txt simply has the name of each student at my university. We'll assume for the moment that they're unique. And a record of whether of which year they're in. Sophomore, junior, senior. And note that this is what is technically called a 1 to n table, because while each student will only appear once, Johnson is only in the table once because she's a single student. But on the right-hand side, sophomore can appear many times. Freshman can appear probably more times than that because they drop out. And so this is a relation that gets a unique key, the student's identifier, and connects it to a piece of information that might be repeated many times in the table, grouping the students by what year they're in. And on the left, I have a table where each field can repeat many times because it's the enrollment for this semester. And so Smith can appear many times because Smith is currently allowed to take several classes. Smith is not on probation. And on the right-hand side, obviously, each class probably has several students signed up in it. So that's the structure of our data. One table that uniquely lists each student because each student is in only 1 year. They're either a freshman or a sophomore. And then a table that has many, it has each student listed many times, each course listed many times, as it records what courses people registered for. And what I would like to do is I'd like to figure out for each course what the distribution of freshmen, sophomores, juniors, and seniors is in that particular course. Have any of you guys noticed the wackiness that can happen with the distribution of people in a course? Like, it's an upper-level course, but there's like all of these sophomores there that have no idea what they're doing or what's going on, but it has a really cool name, so they signed up for it anyway. In the Georgia Tech Computer Science Department, there was a 1,000 level course, Proofs, that is something fundamental that you need to understand for all the rest of computer science. But it was difficult, so it was full of seniors. People would wait until they were fairly sure that they were going to graduate from Georgia Tech, after all, before they would subject themselves to Dr. Karloff's proofs class. This meant that they went through the entire rest of the curriculum without knowledge that they needed, without kind of meta-knowledge that they needed to really digest everything given to them in the other courses. And so it can be very interesting for each course in your university to get a picture of who's signing up for it and what year. You know, obviously you had an idea by listing it as a 2000 course that sophomores would take it, but it's often very interesting to look at who in fact is taking your course. And what we're trying to avoid here is having to open each line in the semester file, and for every single line we look at in that file, go and walk through the entire file full of students until we find the particular student, using the name to match, until we find the particular student signed up for the course on the current line so that we can find out their year. In case any of you ever run into this terminology, people who like using math instead of English call this an order n times m solution to the problem, by which they also, that's a technical term for a bad solution to the problem. It means that the order of the amount of time that's going to be taken by this solution is n times m, because for each line in the semester file, we're going to hang on to that line and loop through most of the lines, or a good number of the lines in the average case, of the student file. And so if you have a moderate-sized state university, 10,000 students, and the current semester, 10,000 registrations, 10,000 times 10,000, you're going to have to do 100 million operations in order to, or something like, something on the order of 100 million operations in order to get your answer. And that doesn't seem reasonable. There's 10,000 students. There's 10,000 registrations. Surely we shouldn't have to do millions of things to get an answer here. Now, I know that my first example was naive. I know you're thinking, Brandon, why are you opening the file anew every time? It will probably fit into memory, even if you're Ohio State. And I will cede that. I should instead be opening the student's file once, reading it into a list, so that when I look at each line of the semester file, I get to just speed through a list of students that's already in RAM in order to find the year that Jones is in and the year that Smith is in. But note that just because I've come up with a faster way to do each step doesn't change the fact this is a 100 million step solution. This does not change. Merely speeding up a step without changing the number of steps doesn't change the fact that this is an order m times n solution that is going to get very expensive very quickly for realistic data sets. It has the same complexity. To avoid this disastrous performance, we can use the mighty dictionary, this built-in Python data type that typically in code like this, it gets built like this. I start with a dictionary called years, which is empty. For each line in the student's file, I split it into its two pieces. I quoted a little bit of it down at the bottom so you can see the code and the data at the same time. And I tell the years dictionary, when I come back to you later and look up Williams, answer back to me sophomore. When I come back later and look up the key Johnson, remind me that she's a junior. When I say Smith, say freshman back. A dictionary has a key that you ask about and a value, a different piece of data that gets parroted back. And the magic of a dictionary is that no matter how big it gets, it runs at the same speed. If you had 1 million students, your dictionary would run just as fast as the tiny liberal arts college that only has 120 students. It's a data structure that, once it's built, makes asking for a particular student take a constant amount of time that doesn't depend on the size of the data set. And so this is the operation that I'm calling a join. I'm calling it a join because I'm running through this semester table down at the bottom of the screen, and I want to get the limited amount of information that's there, a student and a course, and I want to join in to the consideration I'm making the information from that student's table that I looked at earlier. And joining is a trivial operation once you've built your dictionary. I read a line from semester.txt. I split it into its two constituent fields. And then in that quick, nearly instantaneous operation, I give the year's dictionary the name of the student as the key, and immediately back comes the answer of whether they're a freshman or a sophomore. And so I wind up with an algorithm of a n plus m complexity because the second loop and the dictionary inside of it runs at the same speed regardless of the number of students. I've broken the dependency that one of my loops will slow down as the other set of data gets larger. And so I, in fact, here have achieved the minimum possible complexity for this problem, because to answer the question, I've got to read in every student, and I've got to at least read in every course once. In fact, m plus n is the best I can do. I can't go any faster than to have at least read every piece of data once. And so the dictionary has let me leap directly to an optimal solution that reads every line from students once, reads every line from semester.txt once, and is done. This technique of using a dict or a hash table, by the way, I had to say this because I believe Catherine Devlin to be here. Note that this dict technique is also used in the world's most powerful databases. If you use PostgreSQL, have ever done a join between two tables, have ever asked it to explain how it's doing that complete join, and had this answer come back, it's telling you that it's implementing in C exactly what we just saw in Python. It's going to do a sequential scan on the students table, building a hash or dictionary of all of the entries therein. Then it's going to do a sequential scan on semester, doing a hash join, or as it reads in each entry in this semester's registrations, it just jumps into the hash and immediately gets told, regardless of the number of students, what year a particular student is in. So this is the highest level. I mean, as far as computer science has gotten to date, this is the solution to this problem, and it's right at your fingertips with a built-in data type if you're using Python. Now, I'll note a number of you will be thinking to yourself, but Brandon, you only showed us the loop and left little ellipses where the interesting code goes. How are you going to actually add up the number of freshmen, the number of sophomores in every single class? So for those of you who might be more advanced and want to see one or two more data types, here's the complete solution. I'm going to create something called enrollment, which is a default dict. A default dict, instead of complaining when you access a key it's never seen before, auto-creates an initial value for that key. Here I'm telling it that when I first look up a course, EE 101, if it's not already there, it will instantiate a new counter object in order to occupy that key slot. What is a counter? I'm glad you asked. It is another built-in type in the Python standard library, which is a default dict that always starts with 0 and has some special methods on it to make it very efficient to keep for each key a count of the number of times that you've seen it. And so, in this case, having created a default dict whose items are themselves a dictionary, the actual counting is a single line. It's down there at the bottom. I ask this enrollment dict, look up the course, and I either get back a fresh counter if this is the first time I've seen EE 101, or I get the counter that's already sitting there and keeping a tally for me. I then ask it, show me the entry for sophomore, which will either be a 0 if I haven't asked about sophomores yet, or it will be the current count of sophomores, and I increment it by 1. By adding those two little lines, one at the top and one inside of that loop, I'm done. The problem is solved in a constant amount of time, or in an amount of time that grows nearly linearly with my input data set. I'm able to look at the courses and see how many people in each class are signed up for it so that I can give that to my curriculum designers and they can see whether their curriculum is working or whether students are constantly taking the classes out of order because they are not properly motivating the students to sign up for the right classes. I should make the caveat here, for those of you who might be new to Python or still learning as programmers, that I must admit, powerful data types do add complexity to a programming language, because a powerful data type creates a rival approach to object orientation. Here are two entirely different ways to represent a list of XY points. In the first case, I've used purely anonymous data structures, a tuple for each XY location inside of a list so that I can have several points. And then I have some sample code that shows what it looks like to visit each of them and compute the distance out to that point. And on the bottom, I have a different way of representing it, where instead of using a tuple for each point, I actually spin up a real object with real attributes. And you'll note the code at the bottom reads a bit more prettily. I can say point.x and point.y rather than having to index into a tuple to get those items out. But note that I have two different ways whenever I quickly run in to implement a problem or hopefully a solution to a problem. I try not to implement problems, but it does happen weekly. Going in to implement a solution, I have to kind of gauge, is this the kind of problem where I can get away with quick anonymous data types, or should I take the time to actually start creating a class to represent each kind of data? Now, I know a number of you are thinking, wait a minute, Brandon, it's not as hard as you've just made it out, so let me quickly admit that there are variants of the approaches I'm laying out. Instead of saying p sub 0 when I want x and p sub 1 when I want y, if I've gone with the tuple option, a lot of people would define constant indexes x and y to make that bottom bit of code a bit more readable. And I see that. That's a possible approach that does make the anonymous data types easier to use. And there's also a built-in type a named tuple which has real attributes, which can eliminate the indexing, the subscripting entirely. When you create a named tuple, you're asking it to write a little class for you that is as quick and as efficient as a tuple, but if you don't want to ask for p sub 0, you can just say .x. If you want sub 1, you can say .y, so that your code is readable, but the individual objects have no more overhead than a normal tuple. But the choice must still be faced. Use bare generic data types, or go to the trouble of defining real classes. Should your points collection just be a plain list, or do you need it to be suited up as a point sequence whose methods you've defined? Should a point be just a plain tuple, or should it be a class where you've actually described how a point behaves? Plain tuples and lists and dicts, in Python, they make it really easy to get started. They make code easy to get started with, and they require no boilerplate. You don't spend your first half hour defining a bunch of classes. But they carry, they, being a tuple or a list, carries with it no record of your intention. The tuple doesn't know that it's busy being a point. So the names so the type doesn't know what kind of thing it is. It's just the name that you assign it to that becomes your only documentation that you meant one tuple to be a point and that you intended another tuple that's running around to represent something else. Error messages, therefore, from generic data structures tend to be less helpful. If I accidentally get a 2D point and pass it to the 3D distance function, a plain tuple is just going to say list index out of range. It doesn't know that sub 2 is where I put my z element. It's just confused. Whereas if I went to the trouble to write this as a class, it can actually tell me, you're trying to access the thing named .z, but this is not a kind of point that does so. And so error messages do tend to be more helpful, and on many projects, it's when I get the first error message, like the one at the top there, and if I don't immediately understand it, I hang my head, conclude that I have written too long, too fast with pure data types, and I go start defining a few classes so that I can remember 30 lines later what each piece of data means. I will note that Java in this respect is almost more Pythonic. You know, the Zen of Python, the thing that, the mantra you see if you say import this at the prompt, it says that there should preferably be one way to do it in Python. They were probably dinging Perl when they wrote that. But in this instance, they're kind of dinging themselves, because in Java, I've watched Java programmers, and for them, the world is a simple. For them, there is one answer to this question. How am I going to represent a point? Every Java programmer I know sits down and writes a point class. So it's very easy there's only one way to get started. Python programmers, in this case, there's two ways, at least, to do it, and you have to watch for the cusp where a problem begins to become too complex for just throwing generic types at it. Whether you use a plain list, though, or hide a list behind a point sequence class, the powerful Python, generic Python data types will usually be behind everything you do in Python. Learn their names, learn their properties, learn how they are used. It is often not, to someone new, it can be very unobvious what a dictionary is for unless somebody shows you. Tuples, lists, dictionaries, and sets. Go and learn them. So for me, a real sine qua non of being productive in a programming language, and Python happens to have this feature, is to have powerful built-in data types that immediately let me get to work on a problem. Now, I should note, there is a third way. Both of my examples, where the point is a tuple and where the point is a class, assumed that the x and y belonged together, because that's what I've been doing for like many years. If I've wanted a point that has an x and a y, I find some way of storing them next to each other in the same location, because that's what feels natural to me. But I have recently been introduced to what all of my scientist friends are doing, which is quite different. They never, from what I can tell, build structures. They keep all of their pieces of data separate. Instead of storing the x-coordinate 3 next to 4 and the 5 next to the 12 that it goes with, they tend to keep them very far apart, in fact, in separate arrays. They'll put all of the x-coordinates one place and all of the coordinates, y-coordinates somewhere else, and then something really weird happens. They write, print the square root of x times x plus y times y, which looks like the normal single variable, the normal floating point expression for distance. Like, if you covered up the rest of the screen and just showed me that print statement, I'd say, oh, well, this is a programmer who set x equal to 3 and y equal to some value like 4, because this in Python is how you multiply floats, add floats, and do a square root. But in return for writing how you would do a process with one element, they can do that process on a million or several million elements. And that's really bizarre. This square root and the squarings and the addition and the square root look like scalar operations, but they in fact scale to be as large as my data set automatically. And this is an approach that's becoming more and more popular to people as they explore data sets. It lets you build huge result arrays with expressions that look both simple and scalar. And there's a lot of people beginning to experiment in a really incredible tool that's gaining a lot of prominence in science called the IPython Notebook, that lets you write Python code in cells that you then hit Shift-Enter and run each of them. And this is how far at any given time you are from having a plot of your data, which is 1 or 2 lines of Python. Here I've defined an x and a y array. Just for fun, I went ahead and am running that vector operation to compute the length of each of those vectors. And then I go ahead and it's 2 lines of code to do a scatter plot with a grid to help me see where the point's set. If you are interested in looking at data, if this idea interests you, I wanted to go ahead and mention it because many, many people are coming to Python each month now to use this specific tool and these particular vector operations. The way things are going at the moment, it is possible that 10 years from now, the majority of Python programmers will be writing Python this way, because it is looking like Python is going to take off in science in a way that it is not yet overwhelming other alternatives in many other industries. So that is actually something I now need, that is becoming a sine qua non, because once I started programming that way, once I started being able to just do 2 or 3 lines of code and have a graph up, it becomes really addictive. And you start to feel like your data is trapped a long way away from your eyes if you then move to a tool set that doesn't get you that ability to quickly get your information up in front of you. So I did want to, especially for those of you new to the ecosystem, point you towards that approach as you continue exploring Python. All right, so I've so far talked about data structures, solving problems, but I want to share a recent story. What should happen in your program when things go wrong? This could also be called exceptions in a flash gap. I volunteered to help some students learn programming over the last week or two at the Hacker School in New York. And one of the students that I sat down with, we wound up really diving into exceptions. And I wanted to show you what happened as we explored them, because I was really surprised by what happened at the end of our investigation. How does an exception work? I'm going to start with a much simpler concept of calling exit and just killing your process at whatever line of code you happen to be sitting on. Sys.exit is violence. Sys.exit just kills right in its tracks your program that you're running. So if F called G but had some lines of code that it was planning to run once G returned, if G calls H but had some more code that it was planning to run when H returned, if H calls sys.exit, the code that would have run had H returned never happens. The entire process at that moment, even though G is waiting for H to return and F is waiting for G to return, everyone instantly gets terminated, memory is returned to the operating system, and your program is over. In the same way, raising an exception, if H needs to raise an error, also propagates back up the chain of calls, killing every single function in its tracks such that no further operations in that function ever get run. The functions simply die, are taken off the stack, and not another line of their code ever executes. It terminates all enclosing calls. The difference being between terminating a program and raising an exception is that you can catch an exception and stop it from propagating out. So if F wants to watch for value errors from G, do something in response to them, and then keep going, it can arrange to survive the exception and to get to run all of its code. A function like G that doesn't care either way has the rest of its code skipped if that exception gets raised by a function that it calls. And so the programmer I was working with, the student, understood this, but wanted to figure out how can their web app they're writing in a framework called Flask return custom JSON errors. Because natively, if deep inside of one of his routines it raised an index error, that traceback was just being delivered to the client. And the problem is he was writing an API for JSON, for clients that talk a protocol called JSON, so he wanted to return data instead. And his code looked something like this. Try to load the user from the database. If I don't get one, here's an error to return. Try to load a project from the database. Oh, if it's not there, here is an error to return. And so I recommended a different approach because I always feel like I'm trapped in C again if I'm writing code that is constantly having to stop to check the previous operation for an error. It gives me flashbacks. I said to him, how about you define a set of custom exceptions that outline everything that can go wrong in your app. In your business logic, raise those exceptions when things go wrong, and we will wrap all of your views in an exception handler that recognizes each of those exceptions and turns it into the appropriate data that the user, the caller of your API will want to see. I told him when he defined the custom exceptions, don't have them all inherit from exception, because then there'll be no catch-all way to name the idea of an exception from this list. Instead, create kind of a generic app error for whatever his application is, and then have all of the others inherit from it, so that you can watch for an app error and actually catch any of them. In the business logic, when you write your dbload function, go ahead and raise one of those special custom-defined exceptions. We will write a routine that knows for any of the dozens of views in your application how each of those conceptual errors, like a permission error, needs to be represented in data returned to the web client. So if we're at that point, if we write that routine and we're now raising all the right exceptions, how do we catch them and call that routine that we just wrote, exception to response, that gets an exception and turns it into a client visible response? How are we going to catch them and call that in every one of the web views? Well, I suggested decorating every single view with a wrapper that catches exceptions and turns them into JSON responses. I put together with the student something like this: a decorator called catch errors that, when it's given a view, wraps the view up in a wrapper. So it's been given the view, but it slyly returns a wrapper function instead that looks like it does almost the same thing. Given some plain arguments and some keyword arguments, it calls the view. But should the view raise any of our app errors, any of those errors that descend or inherit from app error, then we call our special routine that knows how to turn each of those into a consumable error code for the client. And now, every time a view gets written down at the bottom, we're going to, in addition to the other decorators that Flask defines and that the student had defined, we're going to just throw in catch errors as a decorator of the view, and we now know that anything that our application can run into will turn into a data consumable error. We were quite proud. Well, I was a bit proud of the solution. I mean, all you've got to do is add catch errors to every single view ever and never forget, and it works perfectly. Because I was happy because all that error checking code disappears entirely. If getRow can return any of two different errors, doesn't matter. If cloudOpen can raise an exception permission error, doesn't matter. You don't even have to stop and check because of the rule. If an exception is raised, it will kill the current function. Nothing else will get run, so you don't have to return manually by hand for each way that a call that you make could fail. So I illustrated this approach for the student, and then I suddenly sensed that I should go and read the Flask documentation. It's as if the little Armin Ronacher, the author of Flask, it's as though the little Armin Ronacher in each one of us was whispering to me, "Go read my documentation. Go read my documentation." So I went to the Flask docs, which I don't program in Flask, so I hadn't looked at them before much. I searched for the word exception. That took me to this page that I'd never heard of, and instead it said, to implement RESTful APIs, here's an idea. Implement your own exception type and install an error handler for it that produces the errors. What's an error handler, Armin? Oh, I can tell you that if I raise a database error and it kills my view, I can provide you with an alternate view to run that can return a consumable error message? Oh, I guess I didn't need to write all of that code. That big else-if block where I manually run through every single exception, it goes away. Having to remember tediously to put catch errors as a decorator on every single view everywhere in the app without exception, it goes away because Flask handles this case already. For me, a sine qua non of a programming language, if it's going to be my day-to-day productivity language, is pervasive exceptions, not just that they're a tick mark feature of the language that it happens to include, but that it is an actual design pattern in consistent use everywhere from the standard library of the language out to third-party things like web frameworks. Note the significance of what happened here. It is a strong enough design pattern that working years ago in Europe across an ocean, Armin Ronacher established in his code a pattern for how you handle exceptions. I, years later, with no knowledge of that work, sitting with a student last week in New York, built by hand essentially the same solution. Because it's a pattern, an expectation, a procedure, a solution shared as a culture by the entire Python community, and that's significant. When a feature isn't just present in a language, but where the community across oceans and across years of time are using it to solve problems in the same way, that's what makes it easy to jump between projects, to use new open source tools, and be able to understand other people's code bases. I'll make one caveat. By doing that maneuver, defining our own exceptions, letting them kill the view, and then get caught outside of the view, we have made it easier to write code if it wants to bail out on an error. I've presumed that you'd never want to keep going if the user's not there. You'd never want to proceed if you can't fetch your data, and raising exceptions indeed guarantees that you will not. But what about code that wants to keep going? What if the caller is just looking to see if the user is there, but has a plan for what to do otherwise? What if they have a plan for if they can't get to the data right now? Well, then you actually wind up with something that looks actually quite a bit worse than the checking for errors. Before I had to check to see if a fail value was returned. Now I have to throw a try except around every single operation if I want to survive it. This is such a, Python programmers find this code so unattractive that, so if you find it unattractive, you're responding correctly. You're going to be a good Python programmer. That there is another piece of culture that we follow about what if we want the caller to be in charge of whether an exception is the way we report an error. There is a pattern for that. Design pattern built into things like getAttr, which normally raises attribute error. It's a built-in Python function, but you can provide it with a third default value if you'd rather get a value back that you check whether a failure occurred. Doing a dictionary lookup, usually a bad key gets a key error, but you can also run .get with a default value so that you simply get a value back instead of an exception if it's not present. And that's something that you can do in your own calls if you want to support both audiences. Both the audience that's writing code that doesn't want to stop and check anything and just wants to know that it'll be killed in mid-progress if a user is not in the database. But by allowing a default optional keyword to be supplied, you can make your library friendly as well to people that actually want their code to keep going normally and want to check themselves whether you were able to find the data. So, exceptions are a key way that I keep not just my code sane, but myself sane. Finally, this is the most technical of my recent stories. This is the story of loading SSL certificates from strings. I'm going to go through it quickly because the idea here is just to show you the approach that I took when I encountered this problem. An HTTPS connection, if I make it with the HTTPS built-in library, wants, if I'm going to have a client cert that tells the web server who I am, then I need to provide the path to a key file and a certificate file. That means I've got to, like, if I happen to have them in RAM, stop and write them to disk so that I can then have them pulled back off of disk by the SSL library. That meant that I had to deliver, as a first try at this to my client the other day, code that uses the temp file named temporary file context manager to spin up a temporary file, write the data to it and flush to make sure it gets written out and isn't still in a buffer, then makes the connection, then leaves the with statement which auto erases the temporary file. And the client didn't like this because it's awkward, expensive, and puts a bunch of user keys on disk, even if only temporarily, that we might not otherwise have been writing to disk. So my customer demanded an alternative. So of course I Googled Python, SSL, memory. And a sine qua non of my being productive is to use a tool that has a public bug tracker. Because even if the core devs are too busy for something, other people will start helping each other out on the public bug tracker. And it turns out this bug already had a solution that someone's come up with and is trying to get a core dev to look at. It says that this patch allows SSL certificates to be specified for memory rather than files. And I was all like... And then I looked up at the Python version it's targeted for. And I was all like... And so I decided, can I backport the feature? I didn't really even know how the HTTPS connection used the SSL module, how the built-in SSL module related to the C code behind it, and how do you have C code use certs that are in RAM rather than on disk. I looked at HTTPS connection. It just takes the key file and cert file values, doesn't even look at them. It passes them to something called ssl.wrap socket when you connect. All right? What does wrap socket do? It instantiates something called an SSL socket, passes in the key file and the cert file. So I went, this is now in the standard library. I'm reading the raw source code of the standard library. It's on my disk. If you're using a good IDE, just clicking on SSL takes you to the code of the module, and it takes the key file and the cert file, and it creates on this SSL socket object a sort of secret or private attribute called SSL object, which is a C object. It calls the SSL C library and calls something called SSL wrap with the key file and the cert file. And then, this is interesting, it doesn't necessarily immediately do an SSH handshake to actually start the conversation as currently configured. You can tell it, though that's the default, if you tell it do handshake on connect false, then it will wait and leave the connection still an unencrypted connection until you ask it to handshake. All right, what does SSL wrap do? I opened up, I downloaded the Python source code, looked at ssl.c, looked up the SSL wrap name in its table of methods. I was pointed at this function, which basically just checks its argument types and then calls new py SSL object, passing in key file and cert file. And then I finally arrived where something is done. In all of the code for setting up an SSL object, which finally, down here at the bottom, actually makes calls to the open SSL library, it says use private key file and use certificate chain file. And because it chose those two calls, rather than the SSL calls that operate from memory, I'm locked out of providing a client cert that I happen to already possess as a string. As an aside, this is a stupid variable name. And I actually often do this, but I go back and correct it when I discover my mistake. All through all of those layers, it's called the key file. And it is not. It is the name of the key file. It supports none of the methods of a file because it's a string. Try, if what you really have is the file's name, call the variable file name or path, because jumping into any of this code, you might think that was a file-like object. You might think that you could wrap string IO around your key and have it work. You cannot. It was the first thing I tried because of the variable name. So I then looked at this patch because the bug tracker is open and I could see what this other person was working on. And they called not use private key file, but use private key, and not use certificate, but not use certificate file, but simply use certificate. The key being that you have to create something called a BIO, it's like a string IO for OpenSSL, in order to hold and delimit the buffer in memory where the private key and the certificate live. So the way was now open. All I had to do was subclass HTTPS connection and make one of my own that sends do handshake on connect false, so that when I pass none for the certificate and key, it won't go ahead and start the SSL up with me being anonymous. That will give me a chance to grab the connection's SSL socket object's private C SSL object attribute and tell it about my in-memory keys before I then let it do its handshake and identify me to the server I'm connecting to and vice versa. So a sine qua non of me being able to crack really hard problems like this, when I need to get something done and the whole design of a library is standing in my way of reusing all of its great code for doing SSL, is I need complete object introspection. When things are going south, I need to be able to reach into classes whose assumptions were slightly broken for my case so that I can work around them. It's a polite convention in Python that we generally don't use attributes that start with a leading underscore. The leading underscore warns your fellow Python developers this particular attribute is an implementation detail. You do in Python have freedom. The API caller using your library does decide whether to assume the cost of using an internal detail. If I go in and actually touch underscore SSL object, the trick might not work. There's usually no documentation for what you're doing, and it might break with the very next version of the SSL module because it's making no promise that it's not going to come up with a better way of doing things that involves a different set of back-end variables. But it lets me, for the moment, for this version, get in there, reuse the code, and use the SSL library. I don't have to rewrite the SSL module myself or fork it and keep my own version in my own project. There are several ways to talk to C. You can either use handwritten C code, Python written code, or Swig written code to make an actual shared module compiled in C that lets you talk to a given library. But there are today ways of talking to a C library from Python, C-types, and the more convenient CFFI. But this project kind of already had enough dependencies, if you know what I mean. So since C-types comes built into the standard library, I used it. By the way, another sine qua non, extensibility. Language, let me drop down a level when you can't do something that I need to do. Don't think that you're so complete and wonderful that you trap me. So I explained to C-types, and those of you interested in this, come study the slides later. I explained to it what the internal structure of that underscore SSL object looks like. I explained to it how to create a BIO object, and I was set. I did the thing you're not supposed to do and reached into connection.socket.underscore SSL object, created a pointer to it, created SSL buffers around my certificate and key, and was able to get them loaded in RAM. I was able to go behind the limitations of the standard library when I needed to because of freedom to access all attributes. That means never being limited by what the original author imagined you might want to do. Original authors just have terrible imaginations. It seems every week I think of something I want to do with their library in the standard library or third-party ones, heck, or my own libraries that I wrote last month that were never imagined by the author. One last story. At the Hacker School in New York, I was helping one of the facilitators there, one of the other teachers. She wrote a little regular expression that looks for double words, like the BB in bubble, and that should terminate rather quickly, because whether it's a short string bubble or a long one, you find it at like, what, the second or third character. And so she timed how long it took on short and long strings because of an odd bug she was having, or because her implementation was slow. And she found that it took much, much longer on a longer string. Going back, that's weird because both of these strings I've constructed have a match for a doubled letter 3 characters into the string. And so we looked at this, we spun around, we tried a bunch of different stuff, and I finally just forked the timeit module by copying timeit.py out of the standard library into my own directory and added a print statement it didn't normally have so that I could see what function it constructs in text as a template and then compiles in order to run its timer function. And I'm like, okay, it's checking the time, running my function a few times, checking the time again. It's my code is, what happened to the regular expression? Where there was a \1, there's now an ASCII start of header character, which doesn't appear in my bubble string, so you'd go the whole way to the end of the string and not find it. Oh, look, the string with my code in it doesn't have an R in front of it. it is not a raw string that will pass that \1 through untouched. It's interpreting that as ASCII start of header, thus the weird result. Why was I able to solve that problem? Partly because I could actually briefly fork the standard library, and I am print statement debugger. I don't tend to use PDB. I just add print statements and get the problem solved. And it worked in this case. Well, now, this has not been an advertisement just for Python. Many modern dynamic languages have a number of the features that I've talked about here. But while several programming languages have these features, Python does put them together in a way that is powerful, yet simple and elegant. It's a great place to be, as are several other dynamic languages in use at the moment, if you're using a computer and want to get awesome things done. Thank you very much.